Hello everyone, I am Prem Anand. Welcome to Byte Classroom. You are watching our programming for problem solving series. In this series, we are not going to learn programming just by memorizing the syntax and writing the code. We are going to learn something much more important, how to think, analyze and solve problems like a programmer. So let's continue our journey. In episode 1, we started with a very basic question, why do we need programming? And we understood something important. Programming doesn't actually begin with the code, it begins with the problem. But today, I want to go one step deeper. We know that a problem comes first, but what happens between the problem and the final solution? What exactly happens when a human being thinks about a problem? How do we take something that looks complicated and turn it into something that we can actually solve? And most importantly, how can we develop that same thinking as a programmers? That's what we are going to explore in this episode. So welcome to the programmer's mind. Let's go back to episode 1. We said that programming begins with a problem. Then what happens? We think. From the thinking, we develop steps. Those steps become instruction. The computer follow those instruction and eventually we get a solution. So the overall journey was problem, think, steps, instruction, computer, and then the solution. But today's entire episode is going to focus on one word, think. So, what does it actually mean to think about a problem? Let's find out. And rather than giving your definition, let's start with a small challenge. Okay, no programming for the moment. Forget about C programming language. Forget the syntax. I have a very simple problem for you. Find the tallest student in the classroom. How would you do it? You don't need to tell me the code. Just tell me what you would actually do. Would you do look at everyone? Would you compare the students? Would you somehow keep track of the tallest person you have seen so far? Just think about it. Maybe my assumption will be like a middle, right? So interesting, isn't it? We solved the problem without writing a single line of a code. So something happened in our brain before coding. And that's exactly what I want to understand. Here is the first important idea of today's episode. Problem solving is not as same as coding. Think about the previous challenge. Did you write C? No. But did you solve the problem? Yes. That means problem solving can happen before programming. In fact, good programming starts with the problem solving. We first understand the problem, we think about a solution, and only then we translate that solution into code. So coding is one step in the programming process. So remember, first solve the problem, then write the code. Your first programming tool is not the keyboard, it is your thinking. But when a problem becomes big, thinking about the entire problem at once can become difficult. Let's take a real world problem. Suppose I say I want to travel to Bangalore from Chennai. Is that a complete problem? Not really, right? So immediately several smaller questions appear. When should I go? How should I travel? What's my budget? Maybe there are even more questions. So what we naturally do? We took one big problem and broke it into smaller problems. Then we can deal with each smaller part. Finally, we bring those decisions together. So this is problem decomposition. We break a complex problem into a manageable parts, and this is not something unique to programming. Humans already do this naturally, right? So let's turn what we just did into a systematic process. When a programmer receives a problem, the first question isn't what code should I write? Instead, first understand the problem, then break it down, solve the smaller parts, combine those ideas, and finally check the result. Only then do we have a solution. So don't attack a complicated problem at once. Think systematically. Good programmers don't necessarily think faster, they think systematically, and that leads to a very common mistake beginners make. Here's something I see very often with beginners. They receive a problem, immediately open the code editor and start typing if for printf. Then they run the program. It doesn't work. They change something, run again, change something else, and eventually they make it the answer. But nowadays, straightly typing the question in LLMs like ChatGPT, Claude, DeepSeek, Perplexity, and we got the output. But that's not a good problem solving process, right? Instead, understand, think, design, code, and then test. Your keyboard should not be faster than your thinking. That's a sentence I want you to remember throughout this entire series. So, how do we actually begin understanding a programming problem? Again, let's start with a very simple model. Whenever you see a problem, ask three questions. What do I have? That's your input. What should I do? That's your process. What should I produce? That will be your output. So we have input, process, and then output. So this is a very simple way of looking at a programming problem before writing code. So our problem is like find the area of a rectangle. Before writing code, let's identify our three components. So what will be the input here? Let's assume length equal to 10 centimeter, width equal to 5 centimeter. So what will be the process? So by default, the question arises like what's the area of a rectangle? So it will be like length into width. So what will be the output then? Area equal to 50. Did you notice something? We haven't written any code, but we already understand the structure of the problem. That's a habit I want you people to develop. Suppose if I change the length instead of a 10 to 20 and width instead of 5 to 8, do you need a completely new logic? No, right? The value changes, the logic remains same, and this same pattern is not limited to mathematical problems. Let's look at something you use every day. Take an ATM. What's the input for this? Card, PIN, and amount. What happens inside? The system verifies us and process the transaction. So what will be the output? Cash, or you will be getting some kind of a error. Now think about food delivery. Input, order, and the location. Process, payment, and the delivery notification. What will be the output then? At last, food, right? So whether we are talking about a rectangle or ATM or a food delivery application, input, process, output is everywhere. So once you learn to see input, process, output, you start seeing programs everywhere. But there is another important question. Before solving a problem, don't just ask how to solve it. First, ask what is given. So, what information do I have? Second, what is required? What exactly do I need to find? Third, what are the constraints? Are there any restrictions on the input? Fourth, are there special cases? What happens with zero, negative values, equal values? And finally, what should be the output looks like? A number, a message, or some multiple values? So these questions force us to understand the problem before designing the solution. Let us see what happens if we don't ask these questions. So here is a simple problem. Again, find the largest number. Sounds easy, right? But is this a problem complete? Largest among how many numbers? 2, 3, 100. So what type of numbers? Integers, floats, or complex numbers? Can they be negative? What if two numbers are equal? Suddenly, our one-line problem has produced several questions. And this is important. A simple problem may hide important questions. If we misunderstand the problem, even a perfectly written program can be wrong. So let's make the problem precise. Let's improve our problem. Instead of saying find the largest number, let's say given three numbers, find the largest number. Much better, right? So now we know exactly how many numbers we are dealing with. Our inputs are three numbers. Our output is the largest number. But we should still think about special cases. What if two numbers are equal? What if all the three numbers are equal? What if all the three numbers are negative? This is what it means to refine a problem. The clearer the problem, the clearer the path to the solution. Now, the problem is clear. Let's solve it about writing a code. Our three numbers are 25, 17, and 42. How would you solve this as a human? So first compare 25 and 17. 25 is larger. So for now, I keep 25 as my largest. Now I compare 25 with the remaining number 42. So now 42 is larger. So I update my largest value to 42, and therefore the answer will be like a 42, right? Did you notice no code here, no C programming language, just logical thinking? But now I want to notice something much more important. We don't want to method that works only for 25, 17, and 42. Suppose tomorrow I will give you 10, 50, 20. Will our thinking still work? Yes. And what about minus 5, minus 2, minus 10? Again, yes. So we are not interested in memorizing the answer like 42 is the largest. We are interested in understanding the method. We take our example, identify the logic, generalize the steps, and now we have a method that works for any three number. Don't memorize the answer, just understand the method. But there is one major difference between us and a computer. Humans are very good at solving problems. We use our experiences, we make assumptions, we use some common sense, we understand the context. For example, if someone tells you close the door, you usually understand which door they are talking about. You don't need a 20-line instruction. But a computer is different. A computer follows instruction. It needs precision. It doesn't simply guess what we mean, it needs explicit logic. And that's why programming is interesting. We have to take our human thinking and express it precisely enough for a computer. Think creatively like a human, express precisely like a computer. And once we have a solution, there is still one more thing we have to do. Suppose we designed our solution. Are we done? No. We need to test it. Start with a normal case, then try the boundary case, and then try an unusual case. For our largest number problem, we have tried with a 25, 17, and 42, I guess. Then try with 30, 30, 20. So then try again with minus 5, minus 2, minus 10. Then lastly, perhaps 0, 0, 0. Why? Because a solution that works for one example is not necessarily a correct general solution. A solution is not complete until we test it. This habit becomes extremely important in coding tests and placement interviews. Getting the sample output is not enough. Your logic must handle different inputs. Now let's put everything we have learned into one complete process. So let's put everything together. Someone gives you a problem. First, understand it. Identify the input. Identify the output. Check the constraints. Break the problem down. Design your solution. Test it. And finally, code. Look at where the code appears almost at the end. That's the intentional. Think first, code later. So if you develop this habit, you will approach programming problems very differently. But now we have one more distinction to make. So there are three words that programmers often use together: problem, algorithm, and then program. But they are not the same. The problem tells us what needs to be solved. The algorithm tells us how can we solve it. And the program tells the computer how to perform that solution. So our journey becomes problem, algorithm, program. Today we have spent the entire episode understanding the first part and preparing ourselves for the second. The problem tells us what, the algorithm tells us how, the program communicates that how to the computer. So naturally our question will be algorithm. So now we arrive at the next step. We have learned how humans approach problems. We have learned to understand a problem. We have learned input, process, output. We have learned to ask questions. We have learned to break down problems. We have learned to generalize our thinking. We have learned to test our solution. But how do we take all this thinking and write it down as a clear sequence of steps? And what is that exactly algorithm, which means what makes a sequence of steps an algorithm? Can we write an algorithm without using C? And how do we eventually convert the algorithm into a program? That's what we will explore in episode 3. So what is an algorithm? So Thanks for watching, and if you found this video helpful, please share it, comment it, and share with your friends.